Hi everyone! In this video we are going to talk about the cyclic structures of monosaccharides, and there's a few different ways that we can draw the cyclic structure as well, so we'll go over that too. But just to start, let's see the different types of cyclic structures we can form with carbohydrates. So let's start with the following. So this molecule doesn't have all of the hydroxy groups that a carbohydrate would have, but we're just going to keep things simple here. So we have an aldehyde on the right and an alcohol on the left. And what we're going to do is react this with acid. And this is going to form a six-membered ring where oxygen is one of the members of the ring. And we have an alcohol group bonded to the carbon next to oxygen. So the ring structure here is called a Pyranose ring. And that's just named after the type of ring there. So it's named after Pyran, which is a simple compound with a six-membered ring, and oxygen is one of the atoms in the ring. But we can also call this product a cyclic hemiacetal. So that's kind of going all the way back to our aldehydes and ketones chapter, right? Now, what if we have one less carbon in our chain? So we have a similar molecule, just one less carbon. We would end up forming a five-membered ring. Again, oxygen would be one of the members of the ring, and we'd end up with an OH group on the carbon next to oxygen. And this would be called a Pyranose ring, and that's named after furan. So you might remember the molecule tetrahydrofuran. Furan is that five-membered ring with an oxygen as one of the members of the ring. So we have these two possibilities, and five and six-membered rings are pretty stable, so this usually works out in our favor. Now let's look at the mechanism for the formation of the Pyranose ring there at the top. So again, we'll just start with our aldehyde on the right, alcohol on the left. And again, we're reacting this with acid. What do you think is going to protonate itself? The carbonyl oxygen. So very similar to other reactions that we've seen. All right, so once that oxygen is protonated, that makes the carbonyl carbon more electrophilic. So we do have a nucleophile on the other side of the chain, that alcohol group. So that is going to attack the carbonyl carbon, moving electrons up to the carbonyl oxygen. And now we have our six-membered ring. Although let's just number everything that's in the ring just to kind of keep ourselves on task here. So just to make sure we didn't lose any carbons, we didn't gain any. Okay, so we've got 1, 2, 3, 4, 5. Oxygen is 6. So the oxygen in the ring is still protonated, so it is positively charged. And then on carbon 1, now we have an alcohol. So in the last step, we're just going to deprotonate the positive oxygen. And that will give us our final structure here, the cyclic hemiacetal. So not too bad. Let's do a practice problem. So let's say we have the following. Can you figure out what the product would be for this reaction here? And you can pause the video and try this on your own first, and then we'll go over it together. Okay, so we know that the first step involves protonation of the carbonyl oxygen. All right, and in the next step, the alcohol oxygen is going to attack the carbonyl carbon. Oh, and I'm going to count how many things are in my ring here because I'm not quite sure. Let's see, 1, 2, 3, 4. Oxygen makes 5. Okay, so this is a 5-membered ring, a Pyranose ring. All right, and it looks like on carbon 3 we have 2 methyl groups. On carbon 1 we have an alcohol group. And our oxygen at position 5 is still protonated. So in our last step, we will deprotonate that oxygen, and that gives us our final product. Okay. So let's look at an actual carbohydrate. So let's look at glucose in particular. So glucose, let's draw that out first. Glucose is an aldose, so it has an aldehyde at the top. And then it has an OH group that is on the right. Then at the next carbon, we have an OH group on the left. Then we have an OH group on the right again. And the last carbon in this middle portion here has an OH group on the right. And then we've got our final carbon at the bottom. Okay, so again, this is D-glucose. And we know it's D-glucose because the OH group on the last chiral carbon there is on the right. So that's what makes it a D-glucose. If it was on the left, what would it be called? L-glucose. Okay, so now let's react this with acid. And we know that the carbonyl or oxygen will protonate itself. Now, at the same time, a base is going to come in and deprotonate that last alcohol group, or not the last one, but the second to last one. And that's going to cause the oxygen to attack the carbonyl carbon at the top and move electrons up to oxygen. So I'm kind of drawing all these steps at once. Your textbook breaks this down a little bit more if you want to look at their figures. Now, what we end up with is, well, let's see. I'm going to draw the chair conformation. Almost forgot what it was called. I wanted to say boat conformation. So we've got our 6-membered ring. So if we count our carbons, we've got 1, 2, 3, 4, 5. And then we have a 6th carbon down below, but oxygen will be the 6th member of our ring. And then I'm just going to number the carbons in my chair conformation. Now, I am going to draw that 6th carbon pointing up, and we'll talk about why that is later on. And then that 6th carbon is bonded to that last alcohol group there. So here, I'll just highlight that for you so you can kind of see where that is. Okay, and then we have to draw the other alcohol groups around the ring. So I'm going to leave carbon 1 for last. Let's focus on the other carbons. So carbon 2, I'm going to draw the alcohol group as equatorial down. On carbon 3, that OH group is equatorial up. On carbon 4, it's equatorial down. We already took care of carbon 5 because that oxygen ended up becoming a part of our ring system. And then we also took care of the last alcohol group that I highlighted in blue. Okay, so now let's go back to carbon 1. So carbon 1 was initially not a chiral center. It was not a stereocenter because it had a double bond to oxygen. So that meant it only had 3 groups that it was bonded to, right? However, once our yellow oxygen bonded to our purple carbon there, carbon 1 became a stereocenter. It was bonded to 4 different groups. So we don't really know if the OH group is up or down, and there's probably equal probability of both. So what we end up with are 2 products. So I'm actually going to redraw our structure down below. Everything stays the same except for carbon 1, the purple carbon. So at carbon 1, the OH group could either be pointing up or down. So if it's pointing down, it's in the axial position, and it's trans from our CH2OH group, that I highlighted in blue up above. All right, and this is going to be called the alpha position. Now, we'll get back to that later, though. In the molecule down below, let's say the OH group decided to go in the equatorial position for whatever reason. Then this would be equatorial, and it's cis to CH2OH. That's highlighted in blue up above. Okay, so if the OH group is axial or trans to CH2OH, this would be called alpha D glucose. If it is equatorial or cis to CH2OH, then this would be called beta D glucose. So those 2 purple carbons, let's see, I'm going to use, actually I'll just write down below. The purple carbons are anomeric carbons. Because we have those 2 different positions for the OH group. Now, we would call these 2 different structures anomers. So kind of similar to enantiomers of each other, but they're anomers of each other. And we have the alpha anomer on the top and the beta anomer on the bottom. Okay, now these actually don't form in a 50-50 amount. Let's see, the beta anomer, where the OH group is equatorial, is actually favored. And we do know that equatorial positions for bulky groups are favored in general. So about 63% of the beta anomer is present in solution, and about 37% of the alpha anomer is present in solution. Okay. So this can be kind of complex, so it's okay if you're a little confused at the moment. There is one more way that we could draw these structures, and those are using what's called Haworth projections. Okay, so let's draw glucose again. You'll probably have this structure memorized by the end of the chapter. All right, and this is D-glucose, so the last or second to last OH group should be on the right. Okay, so we already know that we form a six-membered ring. And I'm going to try to draw this from the side. So basically a Haworth projection is sort of a 3D drawing. And we're trying to show here by making these bonds really bold in the front that these bonds are kind of coming out towards us. So they're supposed to be coming out of the plane of the paper. Okay, so now we have to figure out where do all of our groups go. So I'm going to number the carbons again. 1, 2, 3, 4, 5, and 6. And let's do the same on the ring. 1, 2, 3, 4, 5. And we'll figure out where 6 goes in a second. Okay, so the CH2OH group on carbon 5 is going to point up. And then we have to figure out where do all of those OH groups go. So it depends on whether they're on the right or on the left. So the OH groups that are on the right-hand side, I'll highlight in blue. And then the ones that are on the left-hand side, I'll highlight in green. Now remember at carbon 5, that oxygen is actually in the ring now, so we're not going to worry about that one. Okay, so if the OH group is on the right, then it's actually going to point down on the Haworth projection. So let's see, at carbon 2, we have an OH group on the right, so it's going to point down. On carbon 4, we also have an OH group on the right, so that's going to point down. On carbon 3, we have an OH group on the left, so that's going to point up. And then you can also fill in the hydrogens that are there as well. So those will just be opposite. Now remember, carbon 1 is the anomeric carbon, right? So that OH group could either be pointing up or down. Let's just draw beta-D-glucose. So on beta-D-glucose, the OH group would be pointing up. Now, the reason I know that is if we go to our chair conformation on the previous page for beta-D-glucose, we said that the OH group would be equatorial on the anomeric carbon, and it's pointing up. So let's actually translate the Haworth projection to a chair conformation. Let's just kind of see what that would look like. right, so we've got our 6-membered ring with oxygen as one of the members. And the CH2OH group is going to point up, so that's always true for D sugars, so just one of those accepted rules. At carbon 1, we know that we have our anomeric carbon, and we said the OH group is pointing up for beta-D glucose. So that would mean it is in the equatorial position. Hydrogen is in the axial position. At carbon 2, we said that OH was pointing down. If we look at our chair conformation, the downward facing bond is the equatorial bond. Hydrogen would be axial. Carbon 3, we said OH is pointing up. If we look at our chair conformation, the up bond there is the equatorial bond, down is axial. And then at carbon 4, OH is pointing down, which would be equatorial on our chair conformation. Hydrogen is pointing up. So that's how I knew where to draw everything. So if, again, going back to the Fisher projection, if your OH groups are on the right, then they're pointing down on the Haworth projection. And then you can translate that to either equatorial or axial on your chair conformation. It just kind of depends on the chair conformation. Oh, conformation. There we go. It just kind of depends on the structure you're looking at. So here with D-glucose, everything was equatorial pretty much. For other sugars, that might not be the case. Some of the OH groups might be axial, just kind of depending on their position on the chair conformation. So I do recommend going over some of the problems in the book and trying to draw these Haworth projections yourself. See if you get them right. But let's just do a little bit of practice in the meantime. So let's draw the Haworth projection for the following sugar. Okay, see if you can draw the Haworth projection for this sugar, this carbohydrate, once it forms a ring. And when you're done, you can unpause the video and we will go over it together. Okay, so remember there's actually two structures for this one because carbon 1 will become a chiral center. So you could either have alpha or beta anomers for this sugar, but we'll draw both. Okay, so we know that carbon 1 will be our anomeric carbon. And we also know that we'll have a reaction with an acid. So this oxygen on the 5th carbon is going to attack the anomeric carbon there. And then we have protonation of the carbonyl oxygen. So we're going to form a 6-membered ring here. Kind of hard to draw these, so it's okay if it's not perfect. All right, so let's number the carbons in our Haworth projection. And let's see, this is a D sugar because the last OH group there, or the second to last, is on the right. So that means that the CH2OH group on carbon 5 will point up. So that's always true for D sugars. So you can just assume that's going to point up. All right, so now we have to figure out for the other OH groups what's on the right, what's on the left, and how that would correspond to the Haworth projection. So the OH group on carbon 2 is on the right, so that would point down. The hydrogen would point up. And then the next two OH groups are on the left. So those are going to point up. Oh, I shouldn't have chosen purple for that one. Oh well. You get the idea. Okay. And then our yellow oxygen is the one that formed the ring there. Okay, so now again, we have two possibilities here. The alcohol that forms on carbon 1 could either be up or down. So let's draw the second structure here real quick. So we'll draw both anomers, the alpha and the beta anomer. Okay, so let's draw the alpha anomer on the top, and let's draw the beta anomer on the bottom. So for the alpha anomer, would OH point up or would it point down? So would it be trans to CH2OH or would it be cis to CH2OH? So remember, for the alpha anomer, the OH group on carbon 1, the anomeric carbon, would be trans to CH2OH. So that means for our beta anomer, OH will be cis. Oh, I wrote the parentheses a little too early there. Okay. So hopefully this helped you with Haworth projections a little bit. I know it can be a bit confusing. We're also learning a lot of new terms today, so let's actually go over some definitions. So we said for the alpha anomer, OH on the anomeric carbon is axial, but also trans to CH2OH. We said for the beta anomer, OH on the anomeric carbon is equatorial, but that's also cis to CH2OH. Now, what are anomers? So we said that anomers are, well, we didn't really say this, but they are diastereomers because if you notice, let's go back. If you notice, all of the chiral centers stay the same except for carbon 1. So only one of the chiral centers has changed between our anomers. So remember, that would be diastereomers if only one stereocenter changes. So the diastereomers here differ in stereochemistry at the anomeric carbon. Now, there is another term we didn't really talk about today. We might talk about it later on, but you might hear the term epimers. And these are diastereomers that differ in stereochemistry. At a position other than the anomeric carbon. So the anomeric carbon would be the same, but one of the other stereocenters would be different. Another term, we didn't really mention it today, but we will in the future, is mutarotation. And that's the ability for a molecule to flip between the alpha and beta anomers. So you could have a reaction where the alpha anomer converts itself into the beta anomer, and vice versa. Okay, so these are just some words and terms to keep in mind throughout the rest of this chapter. Next time, we're going to start discussing reactions of monosaccharides. So we have alkylation, acylation, etc. So we'll talk about that next.